For the third time in recorded history, an object from beyond our solar system crosses our skies. Three-eyed Atlas, an emerald-tailed wanderer, has slipped past the orbit of Jupiter. Instruments from NASA's Juno spacecraft and Earth-based magnetometers have detected something no comet has ever produced: a sudden magnetic pulse, sharp, ordered, and strong enough to trigger an official agency alert. The odds of such an event occurring at 5 astronomical units are vanishingly small. But what triggered it? And why here, in the deep outskirts of our system? The first alert came from Juno, still circling Jupiter's polar regions after years beyond its prime mission. Its magnetometer registered a sudden deflection, a clean spike rising well above the background fluctuations of the interplanetary magnetic field. At 2214 UTC, the field strength jumped by nearly 35 nanoteslas, an order of magnitude larger than the normal IMF variations at that distance from the Sun. The pulse lasted less than 2 minutes before settling back into baseline values. At Jupiter's orbit, the interplanetary magnetic field normally measures less than a single nanotesla, faint traces stretched thin by distance from the Sun. For Juno to log a deflection of 35 nanoteslas was not just unusual, it was extreme, comparable to what spacecraft record during strong solar storms closer to Earth. Yet no storm was in progress. Out here, in the quiet suburbs of the solar system, the spike stood out as a statistical impossibility, the kind of reading that should not exist without an obvious driver. Hours later, ESA's solar orbiter, positioned inward at 0.7 astronomical units, recorded a subtle echo of the same disturbance. When analysts backpropagated the timing, both detections traced to a narrow sector of space intersecting the trajectory of Three-eyed Atlas. The profile of the signal did not match common solar drivers. No coronal mass ejection was en route, no fast stream from a coronal hole, and the sharp, coherent onset contrasted with the ragged edges of typical solar wind turbulence. For veteran heliophysicists, the event recalled only a few precedents: the disconnection of Comet Encke's tail in 2007, when a solar storm sliced its ion trail in real time, and the enigmatic distortions Hale-Bopp carried far into the outer system. But Atlas was not caught in a storm. Its pulse came unprovoked, out of the silence. Yet the geometry of this encounter makes the anomaly even harder to explain. By October, Three-eyed on Atlas had cleared perihelion and now traveled near 5 astronomical units, a corridor dominated by Jupiter's magnetotail and the turbulent interface between solar wind streams. Its path took it just above the orbital plane, placing it in a region where charged particles can twist and fold under competing currents. From Earth, the geometry proved unforgiving. The object lay close to solar elongation limits, just a few degrees from the Sun's glare. Optical telescopes struggled. Against daylight scattering, and even high-resolution spectrographs could not achieve clean isolation. Ground-based data fell away, leaving the burden of observation to a handful of distant spacecraft. Juno had the most direct vantage, its orbit sweeping through the same heliospheric sector as Atlas. Solar Orbiter contributed a complementary line, though its position nearer to the Sun meant it caught only the faint edge of the pulse. Between the two, a narrow observational corridor opened, small, fragile, and temporary. Geometry like this has crippled observations before. When sun-grazing comets skimmed the corona in past decades, Earth's telescopes were often blind, leaving SOHO and stereo as the only sentinels. During Parker Solar Probe's perihelion dives, solar glare similarly erased most ground-based tracking. Now Atlas imposed the same conditions at 5 astronomical units. For planetary science, it meant the data chain rested on 2 spacecraft alone, a single malfunction, a missed relay, and the pulse would become little more than rumor. Mission planners describe this as a blackout interval, not of technology, but of geometry. For several weeks, Earth's instruments would be nearly blind to Atlas, dependent entirely on what these few orbiters could capture. Timing mattered, cadence mattered, and every anomaly packet had to survive the bottleneck of deep space relays. And just as our view narrows, Three-eyed Atlas reveals its strangest signature yet. Three-eyed Atlas has never behaved like a conventional comet. From its earliest detections, its coma chemistry defied the models. Spectroscopy revealed carbon dioxide dominating at an 8-to-1 ratio over water vapor, a fingerprint unseen in the comets of our own system. Its coma burned emerald green, spectral peaks near 516 nanometers stronger than any C2 Swan band could explain. Brightness records only deepened the mystery. Instead of irregular outgassing, Atlas brightened and dimmed in pulses, sharp and rhythmic. Citizen astronomers in India and Spain confirmed the cadence: flare, plateau, decay, repeat, each interval nearly identical in length. No ordinary jet could sustain such timing across weeks of travel. Regularity in comets is almost unheard of. Their jets vent as surfaces crack and reform, producing chaotic bursts that defy prediction. Even Comet 67P, tracked for years by Rosetta, showed only loose patterns in its eruptions. Atlas, by contrast, brightened like a metronome, each flare repeating with clockwork precision. Observers likened it less to a comet's outgassing than to a heartbeat, steady, mechanical, and sustained across millions of kilometers. The implication was clear. Something about Atlas was dictating order where randomness should reign. Astrometry added yet another oddity. Small microaccelerations, nudges against the predicted orbit, appeared in lockstep with the brightness pulses. Each flicker of light carried a tiny shove, as though illumination and momentum were linked. Planetary scientists debated trapped volatiles, deep reservoirs, or crust fractures, but no consensus held. Now the dossier has gained a fourth entry. The magnetic pulse logged near Jupiter's orbit arrived in perfect alignment with another optical surge. A spike in brightness, a shove in trajectory, and a ripple in the magnetic field, all unfolding within the same narrow window. If light and motion were already coupled, could magnetism now be part of the same chain? When comets meet the solar wind, interactions are expected. Their ion tails act as natural antennas, charged plasma carving narrow conduits through the interplanetary field. Sometimes these connections rupture, as in the dramatic tail disconnections recorded from Enki and Lovejoy, where solar storms literally severed plasma streams. At other times, induced currents ripple through the coma, faint oscillations easily lost in background noise. The Atlas pulse fits neither category. At 5 astronomical units, the solar wind is slower, thinner, less capable of dramatic outbursts. No coronal mass ejection was on record at the time. Parker's solar probe confirmed calm conditions near the Sun, and DSCOVUR at Earth's orbit reported nothing out of the ordinary. The environment was steady. Only Atlas moved differently. Equally strange was the pulse's character. The rise was sharp, the plateau level, the decay clean, as if switched on and off. Plasma models tested at NASA's CCMC could not replicate the profile, no matter the dust size or gas density input. The duration, too, nearly 2 minutes, exceeded the flutter of common turbulence. Scientists now describe it as an outlier, a magnetic signal without precedent in cometary physics. And its coincidence with optical and orbital shifts points to a mechanism still missing from the textbooks. Faced with this puzzle, NASA and ESA turned to their instruments for high-cadence answers. Inside Juno's control teams, the anomaly triggered a rapid shift in priorities. The spacecraft, designed to probe Jupiter's atmosphere and magnetosphere, was suddenly tasked with monitoring an interstellar visitor. Its magnetometers and plasma instruments were placed in high-cadence mode, logging field variations at sub-second intervals. Data volumes soared, but engineers prioritized every packet. ESA's solar orbiter, though far closer to the Sun, adjusted its schedules to capture corroborating IMF data, while NASA's Parker Solar Probe ran comparative sweeps to confirm quiet solar conditions. This triangulation provided the baseline. The pulse had not originated from the Sun, but from the region intersecting Atlas. On Earth, the Deep Space Network reconfigured bandwidth, funneling anomaly packets through redundant channels. Every magnetic trace and optical log was stamped, duplicated, and archived across European and American ground stations. Inside mission centers, operators followed decision ladders reminiscent of NASA's Red Watch crews. Branching, protocols dictating when to escalate, when to safe instruments, and when to broadcast preliminary alerts. The stakes were clear. If the pulse repeated, confirmation would hinge on clean, synchronized data from multiple spacecraft. For now, the anomaly sat in a growing queue of flagged events, debated in late-night teleconferences, its origin unresolved. But the first outsider to spot the anomaly wasn't an agency at all. Thousands of kilometers from mission control, the anomaly was echoed in an unlikely place, a modest radio telescope array operated by amateur astronomers in northern Chile. Designed to scan the skies for transient bursts, the array recorded a repeating hiss in the VHF band at nearly the same moment Juno logged its magnetic spike. At first dismissed as interference, the signal showed a rhythm, short bursts separated by nearly identical intervals. The operators, familiar with local noise, flagged the file and uploaded it to the International Amateur Radio Network. Within hours, their submission was cross-checked against magnetometer data in public archives. The timestamp aligned to within seconds of the Atlas event. NASA analysts later confirmed that the static did not originate from Earth-based transmissions. Its frequency drift matched plasma turbulence near Jupiter's orbit, strengthening the case that Atlas itself was involved. What began as a backyard recording quickly became a footnote in the official anomaly record. For the citizen astronomers, the experience mirrored other moments in history, where amateurs caught the first whispers of the extraordinary: Shoemaker-Levy impacts, supernovae, and meteor storms. Their contribution reminded the Global Watch that the frontier is not limited to government instruments alone. With both professional and amateur eyes aligned, the question became inescapable. What mechanism could drive such a pulse? The first explanation stayed close to physics. One model proposed that charged dust grains carried in Atlas's massive coma accumulated static as they interacted with the solar wind. A sudden release could have produced a coherent magnetic ripple, an en masse discharge rather than random jets. A second theory focused on chemistry. With carbon dioxide outgassing at ratios unseen in solar system comets, interactions between CO2 ions and solar wind protons may have created a transient plasma instability, a resonance that briefly amplified the local field. This would be uncharted territory, but not beyond possibility. To test the idea, NASA's Community Coordinated Modeling Center ran solar wind simulations using exaggerated carbon dioxide values. Yet even under extreme inputs, the models failed to generate a pulse with Atlas's clean plateau and sudden decay. The results highlighted a gap in cometary plasma theory. Either interstellar chemistry obeys rules not yet written into our equations, or the assumptions themselves are incomplete. In both cases, Atlas was forcing science to stretch beyond its comfort zone, exposing limits we rarely confront. The third hypothesis turned to composition itself. Interstellar ices, forged under conditions colder and darker than the Oort cloud, might behave unpredictably when exposed to sunlight at 5 astronomical units. Volatile pockets could erupt in disciplined bursts, releasing both gas and magnetic perturbations. Analogies were drawn to Encke's disconnection and Hale-Bopp's plasma structures, but none occurred so far from the Sun or with such clarity. The scientific consensus was cautious. Each model could explain part of the data, but none could replicate the precision timing, the sharp rise and fall, or the alignment with brightness surges. And yet, the precision of the pulse refuses to settle into chance. Not every scientist was satisfied with natural models. A minority within the discussion raised a speculative, carefully labeled hypothesis. What if the synchronized pulses and microaccelerations were not accidents of volatile release, but signs of regulation? The argument ran that such coherence, a magnetic pulse, an optical surge, and a measurable shove in orbit all arriving in sequence suggests something more systematic than chaos. In this view, Atlas might not be acting as a comet at all, but as a device responding to external conditions. The phrase whispered in conference calls was, "built, not born." Engineers pointed to the clean onset and decay of the pulse as hallmarks of an artificial switch, not a natural flare. If such mechanisms existed, they could, in theory, manipulate magnetic fields for propulsion, communication, or stabilization. Yet every speculative claim was met with caution. Mainstream consensus insists on exhausting natural explanations before entertaining exotic ones. No single anomaly, no matter how precise, can justify extraordinary conclusions. Only converging evidence, confirmed across independent instruments, could push the case beyond cometary physics into something engineered. The debate sharpened, but the official line remained clear. Anomaly, yes. Interpretation, pending. For that reason, agencies imposed strict lockdown on the data flow. NASA, ESA, and JAXA quickly activated their highest anomaly protocols. All data packets tied to the pulse were mirrored across multiple servers, hashed for integrity, and flagged for priority review. Anomaly packets received redundant storage on both sides of the Atlantic, ensuring no trace could be lost to transmission error. Mission operations imposed a tiered release schedule. Calibration files and baseline readings were published within hours, but high-resolution pulse data awaited triple verification. Public archives carried mirrored entries, but agency memos reminded staff that repeatability would define significance. One pulse, however strange, could not dictate a verdict. Within control rooms, teams prepared 2 pathways. If the event recurred, rapid release pipelines would stream raw, spectra and magnetometer traces into open channels. If not, the anomaly would join the record as a single data point, unexplained but not definitive. Citizen scientists were reminded that correlation does not imply intent, and media lines were drafted to balance transparency with caution. Still, the stakes were impossible to ignore. If natural, Atlas expands the boundaries of cometary physics, forcing models to account for magnetic coherence at 5 astronomical units. If extraordinary, the implications stretch far beyond planetary science. The file remains open. One pulse, near Jupiter, may be the first signpost to a new chapter.